Hello, and welcome. Today we're diving into something really fundamental, a question at the very heart of science. How do we actually test our biggest, most sweeping ideas? How does science really build what we call proof?
I mean, think about it for a second. It sounds impossible, doesn't it? Take a law of physics, like gravity. It's supposed to work everywhere, all the time, for all of history. So how could you ever be sure? Do you have to, check every single corner of the cosmos to make sure it holds up? Okay, let's bring that idea down to earth. To prove a really simple statement like all swans are white, what would you have to do? Logically, you'd need to find and check every single swan that has ever lived, is alive right now, and will ever live. It's an infinite task, and that's the core puzzle that scientists have to deal with.
And this gets us to what you could call the scientist's dilemma. If you can't possibly prove a universal law is true everywhere, how can science ever make progress? Well, it turns out science has this incredibly clever workaround.
And here it is, the elegant solution. Instead of trying to prove a theory is right an infinite number of times, which is impossible, scientists flip the whole problem on its head. Their job is actually to find just one single concrete example that proves the theory wrong. This is the whole idea behind falsification. You don't need to see a million white swans. You just need to find one black swan, and boom, the law that all swans are white is instantly busted.
So how do scientists actually go about creating these potentially theory-busting observations? Well, they use a very specific and very powerful tool. It's kind of the hero of our story today, and it's called the basic statement.
All right, here's the formal definition. I know it sounds a little academic, but the idea behind it is actually super simple. A basic statement is just a statement about one thing happening at one specific place at one specific time. It's not some grand, sweeping claim. It's just a single observable event.
Maybe the best way to get your head around a basic statement is with this analogy. Imagine you're taking a photograph. A photo captures a specific subject in a specific place at a specific moment in time, right? Well, that is exactly what a basic statement does for science. It freezes a single observable event so we can all look at it and examine it.
Now, of course, not just any old photograph will work. For a basic statement to be a valid scientific test, it has to follow a really strict logical blueprint. There are rules you have to follow to take that perfect scientific picture. This shows the setup perfectly. A universal law like all ravens are black basically acts as a prohibition. It says, non-black ravens are forbidden from existing. But the basic statement does the exact opposite. It asserts that the forbidden thing, here's one white raven, actually exists, and that direct contradiction, that's where all its scientific power comes from.
So it all comes down to these two crucial rules. First, you can't logically predict a specific observation just from the universal law itself. The law, all ravens are black, doesn't promise you'll even see a raven in the park today. But, and this is rule 2, your specific observation can contradict that law. It's this one-way relationship that makes it a genuine test and not just a circular argument.
And here's a really important detail. A basic statement has to be what philosophers of science call a singular existential statement. All that means is it has to assert that something exists or that something is happening at a specific time and place. It has to be a positive claim.
Because look at the flip side. A statement of non-existence, like there is no raven here, just can't function as a basic statement. And why is that? Well, think about it. Not seeing a raven doesn't contradict the law that all ravens are black. It doesn't tell you anything at all. Only the positive assertion of seeing a white raven can actually clash with that universal rule.
So when you build a proper basic statement, it's got to have two key parts. First, you need what are called individual concepts. That's just a fancy way of saying these specific coordinates in space and time, the where and the when. And second, you need universal concepts, words like swan or white, to describe the what. You need both to create that complete, testable picture.
Okay, so we've got the logical rules down pat. But a statement that only works on paper is pretty useless, right? For it to matter, it has to pass a real-world test. It has to actually connect with reality.
And this brings us to what are called the two material requirements. First, the event it describes has to be, observable by a person. And second, and this one is super important, the statement has to be intersubjectively testable.
Now, intersubjectively testable sounds complicated, but it's a core idea in science. All it means is that your observation can't just be some private, subjective feeling you had.
Other qualified people have to be able to follow your instructions, run the same experiment, and see the very same thing. This is really the bedrock of scientific objectivity.
And here's where things get a little mind-bending. Because any basic statement can be tested by others, it means that no single observation is ever the final absolute word on anything. Even a fact is, in principle, just another hypothesis that can be challenged and tested further by the rest of the scientific community.
And that leads us to our final and maybe most surprising conclusion of all. If even our most basic observations, our so-called facts, are always open to more testing, then what exactly is a scientific fact?
The source material puts this beautifully. An accepted basic statement isn't some ultimate truth we've uncovered. It's simply a point where scientists, for purely practical reasons, agree to stop the chain of testing, at least for now. It's like a temporary resting place.
So let's just ask the question straight up. When scientists all agree on an observation, yes, that is a white raven, right here, right now, have they discovered an absolute, unshakable piece of truth?
The answer, surprisingly, is no. Accepting a basic statement isn't a discovery of truth, it's a decision. It is a pragmatic agreement made by the scientific community, following the rules, that an observation is solid enough, for the time being, to be used as a tool to test those much bigger theories.
And that really is our final, powerful thought for today. Science isn't built on a foundation of absolute permanent truth, but on a series of carefully made, temporary, and constantly testable agreements. The whole structure is always testing its own foundations. So what does that really tell us about the nature of scientific proof itself?